Hello students, are you able to listen to me? सुनाई दे रहा है आपको? So very good evening to all of you. Yes, so let's begin this session. Yesterday, this was the first part that we had discussed, and today we are going to discuss this second part of casting. So, before starting the session, I have one information for you, and that is, we at Unacademy are conducting this test on 11th November 2020. That is, test your basics, evaluate your basic concept, and boost your GATE and engineering service examination preparation. This is fully free of cost test series. There will be 40 questions of 100 minutes, and in all these streams: mechanical, electronics communication, civil, electrical, computer science, chemical. All India rank for live test takers will be given. The test has been curated by India's top faculties, and yes, detailed test analysis will be there. So guys, please enroll in this test. This is fully free of cost test series, and yes, undoubtedly curated by India's top faculties. Yes. So guys, let's move to our discussion on metal casting that we started yesterday. कल हमने start किया था, आज उसी को हम आगे की तरफ बढ़ाते हैं, right? चलो. Here, last session में जो हमने discuss किया था कि first two stages of shrinkages are compensated by riser. What happens during this first two stages? You see, you are like casting, and suppose you are casting a metal, and another case you are casting an alloy. If you are casting a pure metal, then the first case I am showing you for this pure metal. And second case I am showing you for alloys. So the temperature initially will be this TP, pouring temperature. From pouring temperature, the temperature will reduce and will reach to a temperature that is what we call as freezing temperature. Melting temperature. From melting temperature, you see, this is a pure metal, pure substance. In case of pure substance, latent heat of fusion comes out. Latent heat of fusion जो होता है, that comes out at constant temperature. So this phase change here, what is happening in this range? What is happening in this range? Actually, phase change is happening. Here we are seeing the phase change in this time period. Here on this axis we have shown time, temperature and time. So here phase change is happening and temperature remains constant. This temperature, if let us say is TF, then my dear students, melting temperature is equal to freezing temperature. And then here the temperature that you are seeing at, this temperature is your ambient temperature, is your room temperature. This temperature is your ambient temperature, your room temperature. Here what heat comes out? Degree of superheat. This heat will go out. Degree of superheat. Here what heat will go out? Sensible heat will go out. Now dear students, if you look at this time from here up to this total time here is what we call as total solidification time. This time is what we call as total solidification time. Total solidification time. And this time, look at this carefully. This is what we call as, let me show you, from here up to this time is what we call as local solidification time. Local solidification time. Yes, dear students. Now, if you look at alloy, then there, in case of alloy, again, let us say this temperature is pouring temperature. The temperature will reduce from pouring temperature to a certain temperature. Let us say this is at melting temperature. And now phase change will begin. But here when the phase change is happening, dear students, जब ये फेज चेंज यहाँ हो रहा है तो जिस तरीके से प्योर मेटल के केस में आपने देखा था कि फेज चेंज जो था वो कांस्टेंट टेम्परेचर पे हो रहा था, बट यहाँ फेज चेंज कांस्टेंट टेम्परेचर पे नहीं होगा, यहाँ फेज चेंज होगा इन अ रेंज ऑफ टेम्परेचर. यस, here the phase change will happen in a range of temperature and this will be your TF, freezing temperature, and then this is going to be your ambient temperature, that is the room temperature. Yes, dear student, this is going to be your ambient temperature, room temperature. Here you can see Tm will be greater than Tf. This is where actually the phase change is happening, and here this phase change phenomenon will happen in a range of temperature. Which range? Between Tm and Tf, where Tm is the melting temperature and Tf is the freezing temperature. Yes, dear students, very much clear to all of you. And here also this latent heat of fusion will come out. Now you know that during this first stage of shrinkage, during this, when the temperature reduces from Tp to Tm, Tp to Tm, all the metals undergo contraction. All the liquid metals, when the और alloy, when the temperature reduces from pouring temperature to melting temperature, जब temperature reduce होके pouring से melting पे पहुंचता है तो वो contract होता है, कल डिस्कस किया था. और फर्दर फिर टेम्परेचर जब Tm से कम होके Tf पहुंचता है, मतलब इन्हीं दोनों स्टेज में तो पहले दो स्टेज के श्रिंकेज होते हैं, राइट. यहाँ पे फर्स्ट स्टेज श्रिंकेज होता है, यहाँ पे फर्स्ट स्टेज श्रिंकेज होता है, और इसको आप क्या नाम देते हो? सॉलिड shrinkage. Yes, sorry, liquid shrinkage. I'm sorry here. This is what you call as liquid shrinkage in the first stage when the temperature reduces from Tp to Tm. और यहाँ क्या होता है सेकेंड स्टेज में? फेज चेंज श्रिंकेज. एंड ये जो दोनों श्रिंकेजेज हैं इनको कंपनसेट कौन करता है? These two stages of shrinkages, these two different stages of shrinkages, these first two stages of shrinkages are already yesterday I had discussed, compensated by riser. Means what happens? This is what happens, dear students. Suppose you have this cavity here, mold cavity, and we have a riser here, let us say like this. Okay, so when the metal is, its temperature is reducing, look at on left hand side of your screen, when the temperature is reducing, here whatever metal is there, its volume is decreasing. So during this decrease in the volume of metal, the metal will come back from the riser and will compensate for the first stage of shrinkage as well as the second stage of shrinkage. The first stage of shrinkage as well as the second stage of shrinkage. Yes. Ankaj, why Tm and Tf are equal? Ankaj, have you studied properties of pure substance? Pure metal means pure substance. In that, there will be phase change at constant temperature. You want to know the exact reason that why is it not happening here? Tm greater than Tf, right? Then for that, Ankaj, I will have to take you into the basics of engineering materials. You know, if it is alloy, like let us say copper nickel alloy, yes? And if I am trying to show this to you, I must explain in a beautiful manner so that you understand, Ankaj. By the way, Ankaj, who suggested you to join this class? Can I know? 100% copper. Here it is 100% nickel. Do you know, my dear, the melting temperature of copper? You know, copper melts at 1085 degrees centigrade. Do you know the melting temperature of nickel? 1453 degrees centigrade. Now, suppose if it is pure, if it's pure copper, it will melt at 1085. Above this temperature, it will get superheated, and as the temperature is reduced, you see, solidification will begin, and it will happen at the same temperature. As the temperature will come down and down and down, it will reach like 1085, and solidification will happen at constant temperature. All the different copper atoms will start to bond together in a regular pattern known as unit cell, like a face centered cubic. Yes, and all are the atoms of copper. All these are the atoms of copper. They are all alike. All of the properties are same. So yes, whatever the loss of internal energy one atom will be undergoing, the same amount of loss of internal energy another atom will undergo to bond together. Yes, everything will happen in equilibrium at constant temperature. But suppose you take 50% copper or 40% copper, or so let us say 60% copper and 40% nickel, you know, that alloy will neither start to solidify or liquefy or 1453 और neither nor at 1085. ना तो वो 1453 पे होना चालू होगा, ना तो वो 1085 पे होना चालू होगा. क्यों? क्योंकि वहां कॉपर के अलावे लैटिस में निकल के भी एटम्स हैं. Yes, now they are trying to bond together and they are trying to fit together in a regular pattern, and they want to form a face centered cubic cell like this. Yes, now what the nickel atom will say that as soon as the temperature, this is the composition, na? Let us say 60% copper and 40% nickel here. Now this composition will neither start to solidify at 1453 nor start to melt at 1085. Why? Because apart from copper there is 40% nickel here. Yes. Now when suppose you are cooling it down, this system has been superheated to this temperature and you are cooling it down and down and down. As soon as the temperature will reach 1453, the nickel atoms, the nickel atoms, they will say that कि hello copper, देखो मैं तो 1453 पे ही सब एटम, निकल वाले जो एटम्स हैं, हम सब लोग तो मिलके यूनिट सेल बना सकते थे 1453 पे, but there will be copper atoms as well. Copper atoms will say, no, dear nickel, we will crystallize, we will start forming unit cell at 1085 degrees centigrade. You please wait. Then temperature will come down, still no unit cell formation started. And until the unit cell formation starts, you can't say that solidification has begun. The beginning of solidification is the beginning of the formation of the unit cell. Copper atoms 60% will resist the nickel atoms in coming together and forming a regular pattern known as unit cell. So at 1453 degrees centigrade, solidification will not begin. Temperature will further come down, like this temperature will come. Now you see temperature has become so low as compared to that of 1453 degrees centigrade. Now whatever the internal energies those nickel atoms possess, they will start dominating that of the copper atoms, and instead copper atoms will say that no, you cannot form unit cell. Nickel atoms will start forming the unit cells. Yes, now because the temperature has reached even below 1453 and few of these copper atoms will start even participating in those unit cells which are there in vicinity. Yes, इसको पकड़ पकड़ के बोलेगा इधर आ कॉपर, तू अकेला है, इधर आ, चल बनाते यूनिट सेल, जल्दी आ इधर. आर यू गेटिंग दिस अंकज, दिस फेनोमेनन? और ये सब बहुत प्यार से समझना है ना, मैंने आपको स्टोरी समझाई है अंकज. रियल मैकेनिज्म, इसके पीछे का रियल मैथ देखना है ना, सब्सक्रिप्शन लो, आओ इंजीनियरिंग मटेरियल्स पढ़ो, कभी आओ हवेली पे और देखो इंजीनियरिंग मटेरियल्स होता क्या है. दीज आर ऑल द रीजंस बिहाइंड whatever in metal production engineering. All these regions will be clear only in engineering materials. Yes my dear, I don't have any option to erase all. No problem, I'll do this. Come on, now let's move back to the previous slide. Where were we? Yes, I hope Ankaj it is clear why is it happening. Now you listen to me. What I was telling, this I was explaining on the left hand side of the screen. Look at this left hand side of the screen. During the first stage and second stage, when the liquid in first stage reduces its volume, shrinkage happens. From the riser, molten metal comes back and compensate for the shrinkage. Then when the phase is changing, further there is a reduction in the volume of the material changing the phase. So again the metal from riser comes back and compensates for the first two stages of shrinkages. Yes. Now, if the metal has to come back and compensate for these two stages of shrinkages, if the metal has to come back and compensate for the first two stages of shrinkages, then undoubtedly metal here into the riser must not solidify until this casting has fully solidified, isn't it? That means what? Whatever liquid metal is there in the riser cavity, its solidification time, and whatever liquid metal is there in the casting, its solidification time, let us say Tc. So if the riser's purpose is to fulfill for the first two stage of shrinkages, then the solidification time of riser must be greater than the solidification time of casting. Yes, and for solidification time, let me tell you, and I know you know it already, Kovrinov, a person named as Kovrinov, suggested a formula T is equal to K into V by A whole to the power N. This is the solidification time of liquid in any cavity. Solidification time given by Kovrinov's rule, solidification time given by Kovrinov's rule, solidification time given by Kovrinov suggests that the solidification time of liquid metal in any cavity will be equal to K multiplied by V upon A whole to the power N. Now, here there are a few things that we will have to understand, and there are a few myths that also need to be explained. You see here, this is what we call as K is the solidification constant. This K is solidification constant. Its unit will be second per meter square, and this K value will depend upon all the factors like the type of metal being casted, the type of sand mold that you are using, and the mold metal reaction. How is the molten metal reacting with the sand mold? That is also one thing. So K depends upon several factors. What are the factors? Type of metal being casted. Then my dear student, type of sand mold. Then my dear students, mold metal reaction. This is also on which the solidification constant depend. Now, what is N? N is the exponent, and this exponent value can range anywhere between 1.5 to 2. But till now, whatever you studied this formula, T is equal to K into V by A ka whole square. Na? You were writing N2, but this is not the fact. N value can range anywhere between 1.5 to 2. Suppose it is like not 2, then whatever it is, they will give it to you. Okay? And this was suggested first time by a person named as D. Garmo. Yes, after Kovrinov, and this was found to be very much true practically, that this exponent n value can range anywhere between 1.5 to 2. It's not like the fixed 2 k into v by a का whole square. नहीं, ऐसा नहीं होता है. ठीक है? Now, याद रखना, जनरली तो यही फॉर्मूला यूज करते हो k into v by a का whole square, but n is not always 2. N can vary anywhere between 1.5 to 2. Keep that in mind. This was suggested first time by D. Garmo. Okay? D. Garmo की बुक भी आती है मैन्युफैक्चरिंग की, पढ़ना, बड़ी अच्छी बुक है. चलो. Then, you see, as I told you, the solidification time of riser should be more than solidification time of casting. Then only the riser will be capable of taking care of the first two stages of shrinkages. Right, my dear? So, K into VR upon AR whole square should be greater than K into VC upon AC whole square, where this V is the volume of cavity and A is the surface area of cavity through which heat transfer is taking place. You will only count those areas through which heat transfer takes place. Now, if the riser has to compensate The first two stages of shrinkage is undergone by the metal into the casting. Undoubtedly, the liquid metal whichever is there in the riser cavity must not solidify before the solidification of the original casting. It must solidify after the solidification of the liquid metal into the casting cavity completes. That's how you can say that technically that solidification time of a riser must be more than that of the solidification time of the casting. Otherwise, how can the liquid metal come back and compensate? Point to be noted. So, how will you make it sure that the liquid into the riser cavity solidifies after the solidification of the casting? आप ये कैसे assure करोगे कि riser में जो liquid metal है, let us say this is your riser and this is where the casting cavity is there. Okay, this I had drawn that day, na, beautifully, but I am doing like rough work here. How will you assure that this liquid here solidifies after the solidification of the liquid here? How will you assure that TR is greater than TC? For that, one thing that you can do, whatever the heat transfer is taking place from the surface of the riser, that heat transfer can be minimized. How to minimize the heat transfer? For that, surface area will be minimized. So whenever you design a riser, mostly the risers are always designed for their minimum surface area. You see, risers are always designed for their minimum surface area. Risers are always designed for their minimum surface area for any given volume. Risers are always designed for their minimum surface area for any given volume. This thing you have to keep everything in mind. And now I am going to make you practice a very important question. Yes, from GATE point of view, but this question was asked earlier in engineering service examination. The question is, design and compare two side risers having equal volume, one of which is cylindrical and another one is a square parallel piped. You have to design and compare two side risers which have equal volume, but one of them is cylindrical and one other one is a square parallel pipe. This question is very important for the upcoming GATE examination, though it was asked in engineering service examination. Okay, just a minute. I am seeing your chats, your comments in the YouTube. Come on, I will solve this question for you. This question will not be asked directly into the GATE, but how do you solve this question? From there, so many questions can be framed into the GATE examination. Yes, and let me show you how can they do this. This is what they will do. This is what they will do. First, you see how to solve this question, how to compare this. The first riser that you have, it is like cylindrical. So let us say this cylindrical riser has this radius, which is r, and this height, let us say h. What will be volume of this riser? This is cylindrical riser, so let's write Vc. Undoubtedly this will be pi r square h. or you can write H is equal to VC upon pi r square. Yes, one more thing. What about the surface area of this riser? Surface area of this riser, this area 1 plus this area another 1, this will become 2 pi r square. Yes, plus if you talk about this area, this will become 2 pi r h. Now we can make this AC function independent of the height by replacing h by Vc upon pi r square. Yes? Na, chhod do. So, my dear students, it's my son, don't worry. So, this AC will become 2 pi r square plus, ये pi r and pi r cancelled r, this will be 2 Vc upon r. Yes, we have brought this AC term as a function of r. Yes, and volume. Now, for the surface area to be minimum, देखो, I already told you that risers are always designed for their minimum surface area, है ना? I told you that risers are always designed for their minimum surface area. So you can write that dAc upon this dr, this will become 4 pi r minus 2 Vc upon r square. I am differentiating and equating it to 0. So this will lead to 2 Vc is equal to 4 pi r cube. Now, from here you can write Vc is equal to 2 pi r cube, and what we had written Vc here, pi r square h. Yes, this is what we had written. Vc is equal to pi r square h. So this must be equal to pi r square h as well. Now, dear students, from here, what do you get? From here, you get this. I am writing it here, that this pi r square cancelled, h becomes equal to 2r. Yes, or height or diameter should be equal. This is the conclusion you got from here, that if it is a cylindrical riser, its shape is cylindrical, then its surface area will be minimum. Its surface area will be minimum when this height is equal to this diameter, or this height is equal to this 2 times of radius. Fine, dear students. Now, if you want to write the solidification time, if you want to write the solidification time for this solidification time for this riser can be written as K into Vc upon Ac ka whole square. So that is equal to K into, what is volume? 2 pi r cube upon what is surface area? 2 pi r square plus 2 pi r h, and you already found ki h equals to 2r. So replace this h by 2r. This is going to become 6 pi r square. This AC is going to become 6 pi r square ka whole square. So you can easily see pi and pi will cancel. 2 3 are 6, 3 will be there in the denominator, and r square you cancel r cube. On the top there will be r. So this ultimately you are going to get its solidification time, if it is cylindrical riser, as K into r upon 3 whole square. Yes, dear students, I hope there is no doubt into this. You got the solidification time for the cylindrical riser. For one cylindrical riser which is cylindrical in shape, there will be some volume, and its surface area is minimum, right? Because we already minimized the surface area, and we found ki when the surface area will be minimum. The surface area will be minimum when height and diameter will be equal. Yes, and if it is there, so TC you are going to get like this. And remember, this question was asked in engineering service examination, conventional, and from there they are going to frame a GATE question this year only. Believe me, my dear. Don't think though that it is out of syllabus thing that I am discussing. No, this relation you should remember directly. VVI that I am putting in box, that if it is cylindrical riser, and yes, risers are designed for their minimum surface area, so its solidification time is going to be equal to K into R by 3 ka whole square. K into R by 3 ka whole square. Directly you should remember, that is going to help you a lot. Or K into D by 6 whole square. Yes, K into D by 6 whole square. You should remember it directly, dear students, directly. Now, let us go for designing. Let us go for designing the square parallelopiped riser. The square parallelopiped riser. You know how will the square parallelopiped riser look like? The square parallelopiped riser will look like this. You see? This is how your square parallelopiped riser will look like. This is like one of the side, and let us say this is A, this is A, and this will be the height, that is, let us say H. So A this side, one side, since it is a square parallelopiped, and height is H. Now, how much will be the volume of this square parallelopiped riser? This volume is going to be nothing but A square into H, or you can write H as a function of V and A, that will become Vs upon A square. What will be the surface area of this square parallelopiped riser? This is going to be, you see, this is A square, bottom this is A square, and all the other areas like this, that is the like remaining 4 areas, are going to be A into H. So this area, total area, I'm sorry again, this total area is going to be 2A square plus 4 into A into H. Yes, 2A square plus 4 into A into H. Now you can write AS is equal to 2A square plus 4 into A into, in place of H, what can you write? In place of H, what can you write? Vs upon A square. Yes. So this AS is going to become equal to 2A square plus A से A cancel हो गया, 4Vs upon A. Now, for surface area to be minimum, for the surface area to be minimum, you know dear students, this is going to be DAS upon DA is equal to 4A minus 4Vs upon A square. I differentiated the term, is equal to 0, or from here you are going to get 4Vs is equal to 4AQ, or from here you are going to get Vs is equal to AQ, and this Vs you had already written A square H. So that's how, my dear students, you will be getting A is equal to H. That means if it is a square parallelopiped riser like this, if it is a square parallelopiped riser like this, then its surface area will be minimum if A and H are equal. If it is, look at the last slide, if it is a cylindrical riser, right? If it is a cylindrical riser, then its surface area will be minimum only when height and diameter are equal. And now, as you found the solidification time for this cylindrical casting, the same way you can find the solidification time for this square parallelopiped riser, and let us do that. You see, we can write here the solidification time. Yes, dear students, solidification time for a square parallelopiped riser will become K into Vs upon As whole square, that is K into, what is the volume of a square parallelopiped riser? You see, AQ, just now we had calculated, Vs is equal to AQ, yes, remember, and divide by surface area is 2A square plus 4H, and for minimum surface area you found that A is equal to H. So this H, if you replace here by A, here at top, if you replace this H by A, then this will become 4A square plus 2A square, 6A square na. So this will become 6A square and whole square. So that's how TS will be getting as K into A by 6 ka whole square. Very much clear to all of you. And here how much did you get? Look at the previous slide. You got TC is equal to K into R by 3 whole square. Here you got T S is equal to K into A by 6 ka whole square. One more thing they mentioned in the question. They mentioned in the question that you design a riser having equal volume, right? Means they are saying that the volume of cylindrical riser and volume of this square parallelopiped riser are equal. Yes, they already said this. So let us write it here. Vc is equal to Vs. Now, what is Vc? Remember, for minimum surface area, this Vc was, you see here, 2 pi r cube. Yes, this Vc was 2 pi r cube. Now look at this. Vc is 2 pi r cube is equal to Vs. Vs is how much? This is your Vs. This is your, oh, sorry. This is your Vs. AQ. Yes, this is equal to AQ. Now, from here you can write R upon A ratio will become, don't you think so, 1 by 2 pi whole to the power 1 by 3. Now, let us do the comparison of the two risers. Comparing two risers means what term are you going to compare for the two risers? Undoubtedly, you are going to compare their solidification time, that is TC upon TS. Yes, and this you found it was K into R by 3 ka whole square, and this you found it was K multiplied by A by 6 ka whole square. You look at this. Remember, we had found this solidification time TC, K into R by 3 whole square, K into R by 3 whole square, and this solidification for square parallelopiped, K into A by 6 ka whole square, K into A by 6 ka whole square. Now, if you are going to compare them, so this solidification time will be this ratio. Undoubtedly, you can cancel K by K, and then you can simplify and write Tc upon Ts is equal to R upon 3 into, I think, 6 upon A whole square, and that will become nothing but 4 multiplied by R upon A whole square. Yes, very simple. 3 2 is 6 and 2 square 4. We brought 4 out, 4 into R by A ka whole square, and here you found R by A is equal to 1 by 2 pi whole to the power 1 by 3. So Tc upon Ts will become equal to 4 into R by A ratio is 1 by 2 pi whole to the power 1 by 3 whole square. So this is nothing but Tc upon Ts is equal to 4 multiplied by 1 by 2 pi whole to the power 2 by 3, and you calculate, you are going to get it as 1.17. So what are you going to get is Tc is equal to 1.17 Ts. This is what you got the result. Tc you got 1.17 Ts. This is the result that you got, my dear students. Now, dear students, what do you say? Which one is a better riser? Which one is a better riser? Yes, this is what you got the result. Let me see in the live chat session. Many of you are online. Which riser is better? Which riser is going to be better? Ankaj? I'm waiting. You see, whose solidification time is more? Solidification time of cylindrical is more than a square parallelopiped. So cylindrical riser will be preferred over a square parallelopiped riser. Dear students, if you are planning for your preparation in a disciplined manner, in a disciplined manner. On YouTube you cannot have everything. Yes, you will have to take subscription. I'll suggest you to take, if you are preparing for GATE 21, sorry 22, ESE 21 and ESE 22. Do not wait. This is the very important time period that you are going through. Do not wait. Use this referral code RK007. Subscribe to the Plus platform and come. I will guide you there how to plan your study for the upcoming competitive exams like GATE 21, GATE 22, ESE 21, ESE 22. By the way, myself Rajeev Singh, and I am shaping the young minds like you for past 10 years. People know me as a magician of manufacturing and engineering materials. And yes, you will feel that. Feel free to contact me on this number 76759 So for today, this is the total thing that we have completed. We understood about these things. This was very important session. From here itself questions can be framed. From here itself the questions can be framed. This relation is very important. T is equal to K into V by A whole to the power N. You also came to know one new thing. N can be anywhere between 1.5 and 2. Then we did this question, which is very important. Go home and revise this question. So guys, today session I am completing here, and we will meet into the next session tomorrow sharply at the same time. See you all. Bye bye.